We will start with our second session. Our
Right.
second session will be moderated by Sri Samsuddin Khan from Office of CCA. Over to you, sir.
I invite next speaker is Dr. Gautam Reddy. Gautam Reddy is an assistant professor of the Department of Computer Science and Engineering at the NIT, National Institute of Technology, Andhra Pradesh, NITAP, India. Before that, Dr. Gautam Reddy was an assistant professor at the Department of Computer and Information Security at Sejong University, Seoul, South Korea. Prior to that, Dr. Gautam Reddy was a postdoctoral fellow at the Kindi Center for Computing Research at Qatar University in collaboration with Purdue University. Dr. Gautam Reddy earned his PhD in Computer Science and Engineering from the Kyung Fook National University, South Korea. Dr. Gautam Reddy research interests include information security and cryptography. Dr. Gautam Reddy is mainly involved in research projects related to authentication protocol. I invite for talks Dr. Gautam Reddy on the topics design of security protocols for dynamic charging of electric vehicles. Sir, you may continue and warm welcome for this session.
Thank you for the introduction, sir. It's a pleasure to be here. In fact, it's an honor. The title of my talk is Design of Secure Authentication Protocols for Dynamic Charging of Electric Vehicles. The agenda for today is Introduction to the Electric Vehicles and the motivation behind taking this topic as my research and the objectives of our research and the current status of our research, and then followed by the conclusions. Well, electric vehicles can be considered as relatively a new concept in the world of automotive industry. In fact, this one picture tells you about the advantages of electric vehicles that reduces the pollution by reducing the carbon emissions, also the capital expenditure on investments like that towards the purchasing of the conventional vehicles. Well, according to the statistics or the projections, at least like there could be 130 million electric vehicles by 2030 in the world. In fact, in India also, it is projected that at least 30% of the vehicles to be electric by 2030. In fact, like they expect it to be 100, but it's not possible, right? At the same time, it has also been opening the doors for research in several directions in the field of electric vehicles, as you can see here. And in fact, the Asia, Pacific Asia, okay, is going to be the top domain, like a top application area for these electric vehicles. So according to the Statista, Norway stood in the first place in the adoption of electric vehicles by 2018 itself. So probably by now it could have been changed. But however, the units that have been sold were highest in China, according to 2018. Today, it's even much more than this. But however, most of the Nordic countries have been adopting these EVs very swiftly. When it comes to the challenges or the complaints that the general consumers have been already making were like, something like this. The first thing is purchase price of the electric vehicle itself. At least like in the Indian context, it's too high, despite the fact that the government has been giving several incentives. Driving range, coming to the application area, the driving range is very limited. In fact, even if you charge it fully, you can barely travel for 200 to 300 kilometers. Right. So rise of EVs is quite high, and it's projected to be 130 million by 2030. At least in India also like going to be 30% of the electric vehicles by 2030. And coming to the shares of the electric vehicles around the world is something like this, where the Nordic countries are always stood in the first place, even today also. When it comes to the challenges or the complaints that the consumers have been making, well, something like this, the price is pretty high in the Indian context as well. And the driving range is also quite limited. It stood up to like 300 kilometers on an average. And the infrastructure is also quite poor in India, at least. Coming to the current widely adapted electric vehicle charging technique, that's the static charging. So where the vehicle need to stand and charge for long hauls. And the challenges or the limitations of the static charging were range anxiety, which means again, you can barely or hardly travel up to 300 to 400 kilometers. On long hauls, you'll have to stay for too long to charge your vehicle. And even if you're prepared for that, the infrastructure that is available today is really limited. Like according to the Tata, they have only 1,000 charging stations by this year end. So as a solution for these problems, dynamic charging has been introduced. Even this one also has been implemented in the Nordic countries. I myself has evidence of this one. So the dynamic charging is allowing the users or the electric vehicles to charge while in motion. So you don't really have to stand and charge. At the same time, you can drive as long as you wish. So this is the advantage of dynamic charging. Coming to the various steps that are being involved in the EV dynamic charging is something like this. Well, not every road will be having the charging points enabling the dynamic charging. Only a few lanes will be having this one. So that's the reason, like, you have to find out first the finest position to charge, connect yourself with the charging pads or the roadside units or the infrastructure, and then charge yourself. And once you're done, you will have to disconnect, which means you require to have a wide range of principles or the entities to enable dynamic charging. So coming to the communications or the principles that are being involved in the dynamic charging are like, quite a few, ranging from the electric vehicle all the way up to the smart grid. So this is in fact like, a simple part of this one. However, when it comes to the minute part, there are a few more, such as RSUs and the charging pads, which are playing a critical role in enabling the dynamic charging. So that's the reason, like, we divide it into two parts. The first one is front-end communications, or second one is back-end communications. I myself have been looking for some of the security challenges as well as the efficiency challenges in this EV dynamic charging. The very first one is the privacy preservation, which means there is a high chance that to track the electric vehicle by looking into the parameters that have been shared over this public channels. As you've seen in the previous slides, dynamic charging will become true only when various entities communicate together simultaneously. At the same time, most of these communications happens over the public channels, which means visible to many. So while looking into the parameter shared, there is a high chance that by using the static parameters, we can still trace the vehicles. So it has to be stopped by using or by concealing the real identities with the help of pseudo identities. There is also equally chance given for this replay, data modification, and the impersonation attacks. The replay attacks or the data modification attacks can lead to the impersonation, which means, like, if one vehicle user wanted to charge in the account of other vehicle, it's still possible by using some of the parameters intercepted. So this can also have to be addressed by using the cryptographic primitives that are widely available. Also the forward secrecy, which is going to play a crucial role in terms of the billing. So in the forward secrecy, none of the compromised earlier conversations or the secret keys should lead to the compromisal of the subsequent communications. Equally, we also have the efficiency challenges when we go with the strongest cryptographic primitives. The first one is computation overhead. If you look at some of these entities that are being part of this dynamic charging, they hold really limited computation capacity, such as the charging pads, for example. So it's not really possible for it to process the data with the help of the highly efficient cryptographic primitives. So this can be, like, called as an IoT device as well. So which means we need to explore the lightweight cryptographic primitives. At the same time, it should also provide the secure communications. So this is where the efficiency challenge arises. Also the scalability. The number of devices will keep increasing, and it shouldn't be compromising either the security or the efficiency as well. Well, when it comes to the scalability, it's not just the EVs, it's also the infrastructure. And the communication overhead is also equally important because the communications happens over the public channels and this media is really limited. So we will have to enable or achieve this mutual authentications followed by some of the security properties with the exchange of minimal communication parameters. So these are the few challenges that we have identified so far, and a few more attacks were really possible on this one, especially the DOS attacks that we've seen so far. And by assuming and keeping all these things in our minds, we have designed a network model that looks like this. And this is a 3-layer architecture where the company charging server stands in the core level, and the fog server also is a part of company charging server. When it comes to the applicability level, we have quite a few. The first one is EV, followed by the RSUs, the roadside units, also the charging pads. In fact, these charging pads are the one which provides wireless power transfer to the electric vehicles while driving on them. So like, as you see in the first one, like the step-by-step process of the EV dynamic charging. So this is how it looks like. So the predominant principles of the communicating entities were something like this: CCS, FS, RSU, CPs, and EV. So among all these, the biggest challenge is charging pads. How to deploy the cryptographic primitives, or what primitives should we deploy on the charging pads because of its limited computational capacities. When it comes to the rest of them, it's quite okay. And we have to address some other attacks such as impersonation and data modification attacks when it comes to this fog server and the roadside units, because these are the one which plays crucial role in the initial authentication of the electric vehicles. And later on, the given parameters will have to be communicated with the charging pads effectively to get charged, which means the initial authentication is going to happen between EV and the RSU, and followed by the authentication between EV and CPs to get the services. So our objectives were something like this. So identification, analysis of different techniques for building the protocols, and design secure protocols for constrained and non-constrained environments. As said before, we do have both, like it's a blended mode. We do have both constrained and non-constrained modes. And also we'll have to validate the methodologies by means of analysis and simulations. We do have quite a few tools, also like the mathematical or formal methods to analyze the protocols that we design. When it comes to the phases, we have limited it to 5 in the initial stages. Well, this is the work at the initial stages. The first one is a system initialization phase where we use this public infrastructure. However, we use the elliptical cryptography as a primitive here, and followed by FS and EV registration phases before deploying or before getting the services. The registration phase will have to be done, and then followed by the login and mutual authentication phases. The primitives that we used as a part of designing this protocol were elliptical cryptography, especially for the session key agreements and the authentication purposes between electric vehicle and the fog servers, also the roadside units. And HMACs were used between the EVs and RSUs, and hash chains, which is really lightweight, we consider as, were used between EVs and charging pads. So in the system initialization phase, we took an elliptical and a base point and values and publicized them something else, and which were used by the various entities for subsequent communications, especially for the authentication purposes. The second phase is FS registration phase, the fog server. Well, the fog servers also can be like, ranging from 1 to many. And followed by the EV registration phase. The one point that need to be emphasized over here is, in order to stop or withstand the impersonation attacks, we have used unique parameters for each electric vehicle. So by which means, even if one vehicle compromises, the other one will be fine, right? Which means will not be affected. So the login and mutual authentication phases are also pretty heavy. However, at the end, EV and CPS will be able to mutually authenticate and obtain the services. Well, adversary model is equally important as the protocol. So in this one, we used the predominantly used adversary models called as dual and CK adversary, which tells you that every communication parameter that is being shared over the public channel is exposed, which means there is a possibility for modification at the same time replay. And we perform the security analysis in quite a different ways. The first one is informal security analysis and the formal security analysis. When it comes to the formal security analysis, we used Tamarind as well as the random miracles. And also we used a tool called Cycle, so which gave us the better results. So which was telling us all the parameters shared were quite secure. When it comes to the performance analysis, we used one of the tools called Miracle, which simulates in the environment of server, which means like non-constrained environment, as well as the constrained environment with the help of Raspberry Pi ports. And we found it was satisfactory and they were executed within less time. And we also came up with some of the extended models with salient features with the really lightweight primitives, hash functions, and exclusive operations. When it comes to the salient features, we introduced the seamless EV handover between RSUs, RSU to RSU, so with minimal authentication mechanisms. So this is how it looked like. Well, it's still at its infancy. We are still working on that, and we expect it to be ready by the next month. When it comes to the conclusions, as said, there is equal chance for security and privacy challenges as well as efficiency when it comes to the reason is like, the short contact time between the EVs and the charging pads. At the same time, the computational capacities of these devices were really limited. So hence, we need to look for even better primitives to ensure this dynamic charging in the near future. So that's all for now. Thank you.